Hello again and welcome. Today we're going to be looking at a homemade watt meter. Again, let me be clear, I'm not a ham or CB radio operator, but one of the things I noticed between those two groups is that many of them consider the Bird 43 analog watt meter is the gold standard. Again, if we look at those watt meters, those are rated from the factory at plus or minus 5% of full scale. That means if you have a 100 watt slug, for example, inserted in the meter, it's going to give you plus or minus 5% of 100 watts, or plus or minus 5 watts of uncertainty, and that's assuming that you do everything else right. And if you are working with something other than a 50 ohm load, you need both the forward and reflected power, so you're looking at the cost of 2 slugs. Assuming that your reflected power is lower than the forward, you probably want something of like a 10-to-1 ratio. This is one of my early power sensors. This has a 50 ohm load on this side, and this is just a filter. This is a diode type detector. Of course, there's no way to use this to look at the forward and reflected power. Normally to measure power I'll use my spectrum analyzer and some series attenuators, but again with a system like that we can't look at the forward and reflected power. So my goal for this project was to build something that would work over the range of about 1 megahertz to 50 megahertz. I wanted something that would work inline, that could measure the power to the load, and of course there's always some kind of a mismatch, so some of that power is reflected back to the source. So if you're interested in looking at the power at the load, you'd have to take the forward power and subtract off the reflected power. Meters like the Bird, you probably have to insert a different slug, flip the orientation, and then manually subtract the two. With this project we'd like to do all that automatically. The only thing I'd like to do is measure between roughly 100 milliwatts and about 300 watts. And of course the other feature I'd like is I don't want to use an analog meter. I'd rather have this tie into my PC where I can collect the data. If you look at schematics for lower cost VSWR and watt meters, typically they use a diode detector similar to what this has in it. But for this project I just decided to go with a off-the-shelf detector. These are pretty nice. These are a logarithmic detector. The ICs on these were developed by Analog Devices. I don't know who actually manufactures these. These eval boards came out of China. I tried a few different ones, including the AD8302, the AD307, and the AD310. This is the AD8302 here. It's kind of an interesting chip. You can see it has 2 channels. This device can measure the difference between the two. So again, if we're interested in looking at the power to the load, this does the subtraction for you in hardware, and this also gives you the phase relationship between the two. This is looking at the 8310. Again, these boards cost roughly about $10 a piece, and then what I end up building with is the 8307. When I first started looking at these eval boards, I just used my Marconi RF generator, and then I used my HP bench meter to look at the DC voltage coming out of these. To look at the 2 channels, I started using my lab jack. That's just an off-the-shelf data acquisition system. I think that's a 12-bit converter in the one that I have. More than adequate to give me an idea how these were going to work. It's certainly fast enough. And then this is the final unit. You can see I have 2 SMA connectors here. One for measuring the forward, the other one for the reflected power. There's an on-off switch, and there's an Ethernet port. Other than that, you can see this thing is basically sealed up. There's 2 separate cavities. There's one down below. This is where our 2 eval boards are located, and then the data acquisition system is up on top, along with the battery bank. This is using 4 18650 batteries. The last video I made, I showed putting together this and then I also showed some of the other ones that I had made. This is a couple of them here. I made some larger ones. You can see this one with the load bank. This is an even larger one here. Of course, the goal with building transformers like these is to try to get a flat response. And of course, that's the problem with making this watt meter. These boards come pre-built. They work fine for the most part. So there's really nothing to do with these other than, in this case, you can see I've changed out the low-cost connectors. These are an Amphenol connector that I've replaced. These particular boards I think were shipped with a 100 ohm resistor, and you can see I've paralleled up 205 ohms on these particular boards. That's to give me the 50 ohm input. Of course the chip itself has an input impedance and we have to consider that. Other than that, I didn't make any other changes to this. The same thing with the 8307 board that actually is in this device. I really didn't make any changes to that other than to swap out the connector and change the input impedance. And of course, looking at the software from the PC side, that's not really a big deal either. It really comes down to making the directional coupler. So I've made two different ones. This is one of them here. And if you were to look inside of this, you're going to see something similar. It's just some large ferrite, a lot of wire, and there's two 50 ohm terminators. This is a 19 dB coupler. The directivity at a megahertz is 50 dB. At 25 megahertz it's 30 dB. Because it is a 19 dB coupling, we end up dumping a lot of power into the internal loads. And of course, if we are looking at higher power levels, we have to add a fair amount of attenuation between this and our detectors. Not a big problem. I demonstrated this and it actually works quite well. But I ended up building a second one. This one's a 30 dB coupler. Of course, the problem when you start looking at something like this is we have attenuators coming from the forward and reflected ports going back to our detectors. Those will have a certain amount of error. We also have the attenuators that are mounted between the directional coupler and our spectrum analyzer. All those have an error. I could characterize all those with the VNA, but again, the VNA is going to have a certain amount of error with it as well. So I guess my point is that if we're looking at absolute accuracy, I can't really give you a number for that. What I do know is that if I take my RF generator and I tie that directly into my spectrum analyzer and I do a sweep, those two match very close. As a matter of fact, that RF generator didn't work when I received it, so it needed some repairs, and then it was sent in for calibration, and it does meet the manufacturer's specifications. Another way that we're validating this system, as you can see, I have some mismatch loads. This one, for example, is a 75 ohm resistor. This could be an SWR of 1.5 or return loss of 13.98 dB. I have different ones. Here's a 25. This one's 150. Here's a 200, a 100, and here's a 10 ohm. These are all 2 watt carbon type resistors, and of course they're mounted to an N-style connector. And again, to connect this to the spectrum analyzer, I use a series of attenuators depending on the power amplifier that I'm using. This is one that I purchased off of eBay that was damaged when I received it. I've since repaired it using an attenuator from Barry. This one's rated for 20 dB at 100 watt. The device that's in here is rated for 150. I've added a couple of fans to help cool this thing. Works fairly well at 150 watts. To go up higher, we use larger attenuators. This one, for example, this is rated for 300 watts. So what I'd like to do during this video is give you a demonstration of this setup and hopefully give you some idea what its accuracy is. So let's go ahead and get started. So I'm going to give you a little demonstration of the accuracy of this system. So we're going to start out just connecting the directional coupler directly to the output of our RF generator. Again, I've made up two different couplers. This one is a 30 dB coupler and this one's a 20 dB unit. Again, both of these are using ferrite transformers. For a load, we'll just be using the loads that I've made up for the Nano VNA. Currently we have the 50 ohm standard attached. Looking at the RF generator, you can see we're currently running at 15 megahertz and it's set for a minus 100 dB. You can see our software is displaying a minus 48 dB. That's pretty much the lower end of what we're able to display. Now again, bearing in mind, that's with our 30 dB coupler. So the first thing I'd like to do is just go ahead and turn the power level up a little bit. We'll just take this on up to about 40 dB. And you can see our software is displaying roughly 40.1. We'll take it on up to 30. See, the software is displaying 30.1. And again, we'll go up to 20. And our software is displaying 20.3. Again, that's looking at channel 0 dBm. Channel 1 is the reflected power. And here we are at minus 10 dB. Software is showing minus 10.3. And here we are at 0 dB. Again, this coupler is good down to 1 megahertz. You can see our channel 0 dBm is 0.46 or so. And let's go ahead and take it on up to 30 megahertz. And you can see it's 0.18 or so. Again, we can take the RF level back down. Just set it down to like minus 30 or so. And you can see the software is displaying minus 29.8. And again, we'll take the frequency on down to a megahertz. And you can see our software is minus 29.9. So for the math, the only thing I'm doing is a point slope calculation, and I do that for each individual channel. So I'm not trying to do any kind of linearization. Now the one thing I do have to do is, because I've got these virtual bird meters, these are just a screenshot of an actual bird meter, and then I've overlaid my own needle on top of those. Of course, those scales are not linear, so what I've done is I fit my data to that bird meter, and to get that reasonably close, I've used a fifth order polynomial. So let's go ahead and we'll take the power on up to about 10 dB. And again, the software is displaying roughly 9.9. And now let's go ahead and we'll increase the modulation depth. So again, this is with AM modulation. So currently we're at 0%. Let's just go ahead and take this on up to 10. And we can see the modulation meter is reading basically 10. And try this at a lower number. Here's 1, 2, 3, 4, 6, 8. Here we are at 20, 30, 40, and 50. Of course, it's going to start driving the power down. Here we are at 60%. Let's go ahead and drop the RF level. We'll keep the modulation depth the same. Here we are at 0. And a minus 10. Minus 30. And minus 40. And again, let's go ahead and drop this back down. Or we'll take it up. So here we are at 70. Notice on the software there is a decay setting. We can turn this up to slow down the response of the meter. Here we can see the software is collecting at basically 6,000 samples a second. Of course, I have a hardware filter in there for this, and that's currently set for about 2 kilohertz. We'll go ahead and take the power level back up to 10 dB. And again, the software is displaying roughly 9.9. Now we'll go ahead and remove our load. And let's attach a 24.9 ohm resistor. And this should give us a SWR of roughly 2 to 1. And you can see our software is displaying roughly 1.94 or so to 1. Again, this is with a 100 ohm resistor. Again, this should also be 2 to 1, or 100 divided by 50. And we can see the software is displaying 2.074. Again, we'll take the power level down a little bit. Here we are at 0 dB. See, the SWR is 2.03 or so. Let's just take it down to minus 30. And you can see it's at 2.07 to 1. And let's again change our frequency. Here we are at 1 megahertz, and the SWR is 2.02 to 1. We'll go ahead and change this to a 200 ohm resistor. So give us a SWR of roughly 4 to 1. And you can see our software is displaying roughly 4.05. So here's essentially a 500 ohm resistor. This will give us an SWR of 10 to 1. Again, let's go ahead and increase the power level. And you can see this gives us roughly 9.99 or so to 1. Basically 10 to 1. So I have a Signal Hound BB60C, and I've shown this RF generator attached directly to that spectrum analyzer, and those two basically read spot on with each other. And I've also shown where I put a power amplifier between the RF generator and our coupler here. And then I'll take a large attenuator on the back side of this and then couple that into our spectrum analyzer. And again, the two compare very close. So to measure higher power, I'll place an attenuator between our directional coupler and our detectors. So again, if we use 10 dB here, and this is a 30 dB coupler, it gives us 40 dB total. So 500 watts going through this, it'd give us roughly 50 milliwatts, which would be compatible with our AD8307. Again, inside of these couplers, I'm using this RG393. So essentially that's running right between these two connectors. And then this is threaded down inside of the two transformers. If you're interested in what the directivity of these couplers are, I've posted all that up on the EEVBLOG. So the problem that you run into is when you start looking at higher power levels, I may end up adding, 40-50 dB between this coupler and our Signal Hound. And of course we've also added attenuators here. All those will add to the error of the overall system. So unfortunately we really don't have a good way to know what the actual accuracy of this system is, because even if I were to characterize the attenuators on my vector network analyzer, again, there's still going to be a certain amount of error with that. If you're curious what it looks like if we feed audio into the unit, again, I just have a transistor radio here, and I've got my PC connected to the modulation input of our RF generator. See, the response of the meters is pretty decent. If you're curious if that's really coming from here, it is. On the left we have a small power amplifier, of course our directional coupler. This is a 20 dB attenuator. The back side of this there's a second 10 dB attenuator, and there's an additional 10 dB attenuator that goes off to the signal hound, and of course our detector down here in the front. What we're going to do is increase the power to the amplifier, and then we'll track our detector's performance against our signal hound. This version of the software supports my BB60C signal hound as well as my Marconi RF generator. You can see we're set at 57 dB at 30 megahertz. Let's say we want to increase the power level. Let's say I want to increase that power level off of our generator by 1 dB increments. We're at 56, 55, 54. You can see I currently am plotting the output to the load relative to the signal hound. We're currently outputting roughly 170 milliwatts, and you can see the two are tracking fairly close. Let's go ahead and increase the power level. Here we're at roughly 800 milliwatts. This is currently 5.5 watts. This amplifier is good for maybe 8 or so watts. Let's just go ahead and we'll take it on up a little higher. You can see we're reading roughly 8.2 watts between the two. I'll just go ahead and disconnect the signal hound. And you can see it drops right off. And now we're back to normal. Of course, the power to the load is calculated by looking at the difference between the forward and reflected power. So for example, if I drop the reflected power, you can see the SWR improves quite a bit. Likewise, if I remove the forward power. So again, I could demonstrate this with a larger amplifier. The problem that we run into is that each one of these attenuators has an error associated with it. So I could get our coupler with whatever attenuators we use along with our detector to match whatever these attenuators errors are along with the signal hound. It really doesn't give me an indication what the absolute error is. Well, I think that's going to be it for this video. Hopefully you enjoyed it. Again, if you're interested in finding more information about this project, I posted it up on the EEVBLOG. Again, I have not forgotten about this key sight meter. I was just sidetracked by the time this thing came in. You can see it's still on the wrapper. But I was playing around with this watt meter, and I wanted to get this project kind of finished up. So stay tuned for the next series of videos where we start looking at the key sight 1282. We'll see you then.